Patrick White, who will speak on the Erdos minimum overlap problem. So please go ahead.
All right. Thank you. Well, I guess thank you to Mel for organizing another great CANT. It's nice to be back speaking virtually again. Maybe eventually I'll be able to do this in person. That would be very exciting, but it's great that these exist even online. So thanks to everybody else for great talks today, and finally thanks for everybody who's still here. Yes, this is the last talk of the day, so if you're still here, thank you. It's very polite of you to come see me talk. All right. So for my talk, I'm going to be speaking about a favorite problem of mine, I would definitely say a lesser known problem of Erdos. Still publicized. It appeared in Richard Guy's great book, Unsolved Problems in Number Theory, which if you don't know about, you can go check it out. There's still plenty of unsolved problems in there. But let's just dive in. So the plan today is to just talk about the problem, see some of the past progress that's slightly relevant to my own progress, and I have some new exciting results to talk about as well. Okay, let's begin. So here's the problem. Most likely you don't know about the problem, but if you do, that's wonderful. Start with a positive integer, and we are going to just take a partition of the first 2n positive integers into two equal parts, a and b, and for every integer we are going to define m's number of solutions to a minus b equals lowercase a comes from my first set, the lowercase b comes from the second set. And I'm going to define this capital M of AB as the maximum of sub k's for ranging over all the possible k's. All right, and so now the problem is, how can I make this, or I guess how small can I make this MAB? So what is the minimum of MAB over all equitable partitions of the first 2n integers? And I'm going to call this quantity script M of n. Okay, so why do we even say overlap? Why is the problem called the minimum overlap? Maybe this picture already appeared in your head, but now I'm forcing it to appear in your head. Say we have maybe the simplest possible partition. Set A has the first n, and set B has the second n. Then we can imagine the m sub k's from the last slide as the amount of overlap that I would get if I slid this blue bar under the red bar. And you can see that if I slide the blue bar to the left, I can slide it all the way perfectly under the red bar and get an absolutely massive overlap of n. So this particular partition is it is not a minimizing partition. It's a terrible partition. All right, on the other hand, here's a bit better of a partition. One set I take sort of the middle n elements, and the other set gets the low ones and the high ones. And now you can see if I move the blue set under this red set, the most I'm ever going to be able to get them to overlap is just n over 2. All right, and so already we have a bit of a crude upper bound on the script m of n, and that upper bound is n divided by 2. Okay, so let's move on. Let's see a lower bound now. So if you remember, I guess 2 slides ago, we had it was the overlap was the maximum over all of the k, but there's only so many k that you could actually have solutions to, right? So maybe if I skip back to here, right, for how many k could there be even a single solution? The biggest possible k you could have here is 2n minus 1. The smallest possible k you could have here is negative 2n plus 1. So there are only so many k, and we know that there are n squared pairs a and b. And so now skipping back to this slide, with a little basic pigeonholing, of course, this means that we have a lower bound of n squared divided by 4n minus 2. So there, now we have a at least some lower bound, some upper bound, n over 4, n over 2, essentially. That's what we're working with now. And when Erdős first asked this question in 1955, he actually thought perhaps the answer is just n over 2. Right, and I don't know if I should pause here and give you a second to think which one you think is closer to the truth. Suppose you could do that. It turns out both of these bounds are far from the truth. The truth is actually, it seems, in the middle of this. The lower bound is terrible and the upper bound is terrible. So we need to fix this. All right, and over the years, several authors contributed to this particular problem. And over the years, there were several problems like this. In fact, nowadays, there are a couple problems like this as well, which I'll touch on later, since I think that connection went unnoticed for a little while. Okay.
Do you have pictures? Do you have pictures of the minimizers? That is to say, we've seen that intervals are somehow bad.
Yes,
So,
pictures are coming. Thanks for, great. This looks even better for me now. Pictures are coming. Just give me a few more slides. Sorry, they're not here already. All right.
I mean, one assumes there's a sort of fractalish like look to the minimizers, that they look rather scattered.
Yes.
And they don't have,
yes.
Yeah.
It's honestly, I can't exactly describe exactly why the minimizers look like they look, but there are some prominent features and then other features that are, as you said, a bit disordered or fractally, but we'll come on those very soon. Okay, so when Erdős asked the problem, he of course saw these first two fairly simple bounds, and then lots of other people started thinking about it, I suppose. The first improvement is one that's easy to understand for us. If you think back, as I was just saying about all of these k, you can go as low as negative 2n plus 1 and as high as 2n minus 1. But if you think for a second, there could never be very many solutions a minus b equals 2n minus 1. There could only be one possible solution there. Same with, in general, the number of solutions to a minus b equals 2n minus 2, 2n minus 3. And so necessarily, if we can improve, I guess, the pigeonholing, because the boxes of pigeons at the end of the spectrum necessarily do not have very many pigeons in them. And that's the idea at the heart of this second one. Then a year after, Motzkin, Ralston, and Selfridge sort of disproved Erdős's initial guess of that the answer is actually n², and they proved that it's no more than 0.4n. And for this, they came up with some constructions. It's interesting to note, actually, that the first, you have to go all the way to n equals 15. So a partition of the first 30 integers, first 30 positive integers, in order to find a good enough partition to get as low as 2n over 5. So I think you can sort of understand why maybe the n over 2 at least stood for a few months, that you actually have to go to some fairly non-trivially sized examples to significantly break past the n/2 barrier. Okay, and then Swieczkowski, with a fairly long combinatorial argument, improved the lower bound quite a bit. And then Moser had a great idea, which we're actually going to touch on later, and then significantly improved the lower bound again. And then Jan Christian Haugland, as part of his doctorate research in 1996, sort of nice big breakthrough. He got an award for this, improved the upper bound, and found a fairly robust technique for finding good something close to an optimizer. And we'll touch on that that next. And then in 2016, it's the same method as before, just more computation time. Unfortunately, yeah, I guess his method has some computation in it, and sadly, ultimately, my method has some role played by a computer as well. I would actually, well, we'll touch on this later. I'd love to avoid using a computer, but okay. So we've seen the initial combinatorial number theory statement of the problem, and it's actually useful to sort of take a function perspective on this. And this is actually common of a few problems in combinatorial number theory, where it's just useful to instead have a look at a partition. You have a function that sort of describes the density of where you're choosing numbers from. Okay, so the way we're going to specify our function is f of x, this function that's going to represent that set A from my first slide, will be a function measurable, of course, supported on -1, 1. All of the values are going to be between 0 and 1, and the total mass will be 1. And the total mass condition, of course, just represents that we wanted our set A to have half the elements and our set B to have half the elements. Now our function G will, of course, represent that set B, and G will be 1 minus f. F plus G will be 1. And G will be supported, of course, also on -1, 1. And then now we have a function m of x instead of our m sub k, function m of x defined as this now correlation integral, as they're sometimes called in the literature. Okay, m of x I will call as the overlap function now. All right, we'll say mu is going to be the minimum value of the supremum of this m of x taken over all of the possible f satisfying my above hypothesis. And Swinnerton-Dyer proved that this statement is equivalent to the previous statement where we just had partitions of positive integers, which is of course what you expect, but it was good that we had this result. Okay. So what was Haugland's bound?
I'm sorry.
Yeah.
I didn't understand what n was in the last slide.
So, say again?
What is n when you're taking the limit at the very end?
No,
Oh.
this n is from the previous slide.
That's right.
This n is from the previous setup.
Yes.
Okay.
Was that a good enough explanation? Yeah, I'm sorry. It was the n way over here from the first slide. And if you remember, right, we had these bounds where I had essentially n over 4, and this one, the upper bound was n over 2.
Yes.
And so we know that like it's a linear number of solutions. And so essentially the problem is what is the constant for that linear function?
I mean, it's not just the constant, the measures that are going to be represented by f and g are sort of limits. You can think of them as limits of choices of the discrete sets of the integers.
Mm-hmm. That's correct.
This is a sort of scaling of the problem so that n is gone. That's sort
Absolutely.
of the point. For large n, you shouldn't.
Yeah, absolutely.
That makes sense.
Yeah.
Thank you.
Okay. Yeah. Oh, yeah. Of course. Interruptions are good. Yeah. It means you haven't tuned me out yet. Okay, so next slide. So what was Haugland's idea? I suppose it's a pretty natural try for how to find functions. As I sort of remarked on earlier, in order to get good partitions, you actually have to go to sort of fairly, as I said, n equals 15 to get a good partition. But if we know that these two versions of the problem, the function version and the partition of integers problem are the same, then you can start searching simpler objects that might give you better partitions quite quickly. So Haugland's idea was, I'm going to look for good f among just the simple functions. So I'm going to take my interval -1 to 1 and I'm going to break it up into n pieces, and I'm going to find the best possible f over these simple functions. A fairly simple idea, but definitely effective. In fact, if you just broke the interval into 2 pieces, you can already find an f where the supremum of m is 4 divided by 9, so 0.444. So even like the simplest possible f, other than the just a one-step function, the simplest f improves the n over 2. So it's a good idea. Now the drawback of this idea. So to be clear, what is Haugland doing here? He's written out a quadratic program. And the problem with Haugland's quadratic program is it is not convex, which means it is hard to, well, as if you chose n to be large, it's going to be hard to find that global optimum. You can but in general, it's going to be a slow process. To date, the best n that we're working with is only n equals 51. So it slows down quickly, of course, because there's no fast algorithms to solve this. Now we're just about done talking about the upper bound, because that's not what I focused on. But here we now have a picture of what the best 51 step function looks like, and it shows us that we have an upper bound on the minimum overlap of about 0.38. Okay, let's quickly move on and talk about the lower bounds, because those are the ones that are, I mean, before my work, they were much further from the truth. I believe this 0.38 is fairly close to the, well, my work shows that this is fairly close to the truth. Let's move on. All right, so let's sort of rehash that pigeonhole argument that we had earlier. If you integrate the m of x function, of course, what number are you expecting to get? Well, a little bit of Fubini shows you that, of course, the total mass of m is 1. And so because the supportive m is between -2 and 2, immediately we get this mu is at least 1/4. Now, when could this bound possibly be achieved? Well, if we had the constant function, then it would be achieved. And so the way I think about this problem is, to find good lower bounds, you sort of just have to find these properties that m must have that show you that it cannot be very close to a constant function. And so that was, Moser went a long way in doing this with his method that we're about to see. I can kind of see maybe where his idea came from, but without, maybe you can see where this idea might have come from as well, is these functions sort of look like probability distributions. And so why don't we consider the variance of them? And it is not very much work to get a very nice calculation on the variance of m of x. My apologies here, this -1 and 1 should definitely be a -2 and 2. Okay, so the variance of m cannot be too big. And you can go check, is what would the variance be if I let m be just the constant a quarter? And you'll see that the variance is way too big. It's like 4/3. And so, well, the functions that minimize variance would, of course, be I cluster as much stuff close to the mean as possible. And so this idea shows you, or with this idea, you will obtain immediately that the minimum overlap is at least 1 divided by the square root of 8. So 0.3536. So this was a huge improvement. And this is more or less exactly where the lower bound has stood since Moser's work. Okay, still got a little bit of time. So to improve the lower bound, how do we do it? We need more properties that m of x has to satisfy. And so my new idea that hadn't been tried on before was why don't we...
Sorry to interrupt again. Do you have any idea abstractly how close the minimizer is to being unique? Is that, I mean, I assume that it...
Let's talk about that soon. I'm going to say something. Yes, let's talk about that in a second. And if I don't address your question, ask me again, because it just means I forgot. Okay, I'm sorry. I don't want to get way over 3 p.m. All right, so improve the lower bound. We need more properties of the m of x. My idea was, let's look at the Fourier coefficients. And my motivation here was, if you looked at the integral definition of the m of x, it resembles a convolution, or as I said, a correlation integral. You know, if you just tried the most basic thing, let's just take the Fourier transform, you already get sort of a nice expression of how the Fourier coefficients of m depend on the Fourier coefficients of f. And this is maybe starting to look useful. Now, after I posted my work to the archive, Noah Kravitz, who will be a speaker here tomorrow, I believe, pointed out to me that there's a body of ongoing research dealing with what are called autocorrelations and convolutions, which are related in particular to combinatorial number theory questions coming from questions about sit-on sets. And it seemed that sort of a central tool in that area of research was just also elementary Fourier analysis. So in hindsight, this idea of just use elementary Fourier analysis is obviously not so novel, but it seems that it's a good tool with these sort of types of problems. Anyhow, here's the basic lemma. And when I started working on this, I quickly wrote down this lemma, and because of course it's very easy to obtain. But then it took a little while for me to figure out how do you actually use this lemma to get something. And so I will tell you how I got something out of this lemma, but it is entirely possible that there's a more clever way of pulling something helpful out of this, which I would be very excited to see. Anyhow, here's how I did it. If you notice, if you start this expression here and you plug in any even positive k here, you'll notice that this term here disappears. It's 0, sine of something times pi, right? 0, which shows you that the even Fourier coefficients are negative real numbers. So this is well, that's the heart of the idea. So in particular, if I integrated any of these cosine functions against m, all of them cannot be positive. They're all non-positive numbers. And so this sort of constraint formed the key, the basis of the improvement that I ended up obtaining. And now sort of the dilemma for me was, how do I combine a bunch of these constraints into, to use them all at once? What I came up with was just a linear program where the variables are going to be the average values of m on small intervals. Now, perhaps there's a much cleverer way of doing this that's more analytic and doesn't involve a linear program, and I would be super excited to see that. But anyhow, linear program is what I went with. And I'll now show you the statement of the linear program that shows sort of the basic guts of it, where we also make this assumption where f and m are even functions, which, by the way, I believe is true, but I haven't been able to prove that, to my frustration. So if anybody can prove that if the optimizer is even, if somebody can prove the optimizer is even, I would also be excited, because regrettably and embarrassing, I was not able to do that. Anyhow, here's the linear program, and we can talk about it for a sec. This constraint here is just sort of saying that the mass of my f function has to be 1. This guy here is saying that those Fourier cosine coefficients are non-positive, and this guy right here, this final one here, is actually coming from the Moser variance idea. It turns out including this one is actually extremely important as well. And so you include all of these things together, and now, of course, this is a linear program, so I don't have the problem Haugland had before, and I can make n, this capital N, very big. And in fact, it is absolutely crucial that I make n very big. Otherwise, the improvements are terrible. So improvements start getting good when n is around 2000 and higher. Things are looking up. And then I can improve under the evenness assumption, new, much better lower bound. Okay, now let's touch on, in general, I'm almost done. I know the conference is almost done for day 2. I just said in the previous program, we had all of these, I had to make this evenness assumption, and I wasn't able to prove that the optimizer was even. So how do we get around this? Well, what I did was add more constraints, essentially coming from the original lemma, that deal with the sine Fourier coefficients, and this allows me to remove the evenness assumption. It complicates the program, but it figures that out. And then also I add constraints coming from the odd cosine coefficients, which allows me to improve that lower bound we just showed, the 0.375, a bit more. And I can put it all together in no longer a linear program, but still a convex program, so I can still solve it quickly. And the whole thing looks like this. So it's not crazy complicated, I suppose, but here's just a snapshot of it. I don't want to talk too much about it because it's, well, I don't think that would be overly helpful, but you can still see the variance is over here, the total mass is over here, cosine coefficient constraints over here. Okay.
Sorry to come back to the same question again, but I assume that in these cases you do get a unique optimizer for these.
Yes.
Each
yes. So in a convex program, right? You have.
Right. In theory, it might happen that there's more than one optimizer, but it's unlikely, very unlikely.
Yeah. Well, in general, right? If something's convex, you should have just one optimizer, or.
Well, unless you have, I mean, you can have a polytope where there's a whole face. It's an
Oh,
optimizer,
yes.
It's not a very typical situation.
Yes. Okay. Sorry. Yes, you're absolutely right. And no, yeah, I do believe in these cases, just one. Yeah, just one. Okay. So what happens here? Oh, I guess I wanted to say one more thing before final slide, I guess, is it was very useful to, I have the same variables from before, which are the average values of my m, but I also start controlling the Fourier coefficients of my lowercase f. And because I do this as part of the output of my convex program, I actually get to see what my lower bound technique would give me for the f function. So I can compare my optimizers to the optimizers that come from Haugland's method, which I think is really interesting. Okay, so now let's compare my method to Haugland's method. Let's see the pictures and be done with this talk. So here we go. If you sort of truncate my f to the degree 5 trigonometric polynomial, so just the first 5 Fourier coefficients, and you do the same for Haugland's method, you actually see that they definitely appear to be converging to a similar shape. As well, the optimal M function, the shape of the optimal M function also appears quite clear what it needs to look like. It needs to sort of, at -2, grow slowly, flatten out, and necessarily dip at 0, which I think is also quite fascinating. And then same thing for the other side.
Yeah, it seems clear that there's something that's happening for finite ends that you're not seeing here, right? And then if for finite ends, you have these spikes, which are not visible in the limit, apparently.
Yeah, so I think they're more visible as you start considering the higher degree Fourier approximations. Things start getting, it's hard for me to say exactly what's going on. Things just get messy as I could have given you the figure of the degree 10 approximation, but then it's much harder to see really what the structure is necessarily. And perhaps
it develops spikes.
Yeah, yes. There are absolutely spikes. I guess a way of saying this is that the decay of the coefficients isn't so immediate that it's very smooth. It is not very smooth. But that could also just be sort of imperfections in my program as well. I am not sure. Anyhow, let's conclude this talk. The lower bound that I end up getting is 0.379005. The part of the reason I stopped here is because I wanted to be over 0.379. And that way we can see that now the lower bound and the upper bound are extremely close. Big improvement over the lower bound, which is great. A final comment on what do I think is the truth? I think the truth is very close to 0.38. In terms of what could be improved on sort of my end here, where's the bottleneck? I actually think I have a pretty good, I think in my convex program that I showed you, I have captured just about everything that needs to be captured. I could be so wrong, but I think I've captured everything that needs to be captured. The bottleneck was that because I need to choose n to be so large, I needed to use a numerical convex solver. And so I needed to be sure, because of floating point rounding, I needed to be sure I was away from the boundary of the feasible dual space. And I believe I lose enough that, well, I think I'm losing a little bit there, but that's all I'll say about that. So it is 3:03, so I'll cut it out here. Thanks for your attention and the questions along the way. Those were great.
Thank you very much.
Yeah, thanks.